The show you're about to watch concerns a space shuttle mission unlike any other you've ever seen, the Tethered Satellite Mission. While the mission was successful in proving an idea that had only been a theory, we had some hardware problems, and the tether did not extend as far as we wanted it to go. As often happens in research, we learn from things when they go wrong. Here we learned enough to prove that this truly unique concept really does work. In this program, we do calculations based on the length we expected the tether to extend, not how far it actually extended, so keep this in mind and enjoy the show.
T-minus 10, 9, 8. We have a go for main engine start. We have main engine start. 4, 3, 2, 1, 0, and liftoff. Liftoff of the space shuttle, and it has cleared the tower.
It is slow, that's the case.
Thank your touchdown.
An ordinary summer's day at the lake. The sun, the water, good fun, and physics. Physics? You might not think so, but yes. Take this water skier, for example. There's a lot of basic physics involved in skiing. There's the force of gravity, the pull of the rope, the resistance of the water. The skier balances these forces, and a few more, to keep a stable center of mass gliding across the water. But the physics is so basic, he doesn't even have to think about it. He just skis. And if he doesn't get it right the first time, he tries again until he does. But in space, we usually get only one shot at a task. So, before we do anything, we analyze it to get the physics right the first time. That's important, because what you think should happen in space isn't necessarily what will happen. Let's say we want to speed up the orbiter to rendezvous with a spacecraft just ahead. Do we fire the orbiter's jets to go faster? No. If we follow intuition and fire the jets to speed up, we'll actually be propelled into a higher orbit that will end up slowing us down. So up here in space, we can't always depend on what we think will happen. We have to know what will happen, and that takes a good understanding of physics. Physics, whether we use it to rendezvous with satellites in space or describe water skiing on the Earth, has unlimited applications, and today we have a really unique one to show you. Welcome aboard the Space Shuttle Atlantis, where we're about to launch a new type of spacecraft. It's called the Tethered Satellite. That's because the entire time it's deployed, it remains tethered to the orbiter by a 2-millimeter diameter strand of insulated copper. This is one of the most complex missions ever attempted by a space shuttle crew. What's amazing is that most of the physics that we use to fly the tethered satellite is the same physics that you study in high school. It includes concepts like gravity, angular momentum, and center of mass. In the next few minutes, we're going to see how these concepts relate to the orbiter, the satellite, and the tether. We begin the experiment by deploying the tethered satellite. We do this from the top of a 12-meter boom to protect sensitive parts of the orbiter. Small, invisible nitrogen jets are used to get the satellite and tether in motion. Once they are far enough away from the orbiter, we can turn the jets off, and the satellite and tether will continue to deploy.
What makes the satellites continue to go up? After all, you can't push on the rope. Well, that's where the physics comes in. We take advantage of a force that causes the tether to continue extending on its own, away from the Earth. It's a force that gets stronger as the tether gets longer. But what is this force? Well, it's gravity. Gravity? But how can gravity make things go up? Well, it's one of those things that doesn't make sense until you understand the physics. So let's look at the physics of gravity. All objects are pulled by Earth's gravity, even objects in space. But the further away from the Earth the objects are, the less the Earth's gravity pulls on them. Sir Isaac Newton described the force due to gravity as an inverse square law. That means that an object 2 times as far away from the center of the Earth as another object of the same mass feels only a quarter of the gravitational pull. It's a mouthful, but next to the tether, gravity is the most important influence on our tethered satellite. Let's find out why. We'll calculate using newtons to measure the force. When the 500 kilogram satellite is in the cargo bay, 6,700 kilometers from the center of the Earth, it has a certain amount of force on it. If we extend it 10 kilometers upwards, gravity pulls on it about 13 newtons less. Extending it another 10 kilometers reduces gravity's grip by another 13 newtons for a total of 26. Now we said that gravity is an inverse square force. And for our purposes, the distance involved is from the center of the Earth to our orbiter and to the satellite as it moves away from the orbiter. But the distances the satellite is moving away from the orbiter are much smaller than the distance to the center of the Earth. If we look at the force on these smaller distances, we see that the change in force is linearly proportional to the change in distance. We call this difference in the force of gravity with distance the gravity gradient force, gradients being the mathematical term for difference. When the tether length doubles, the gravity gradient force doubles.
Now we have enough information to understand why the tether reels out and stays out. So, let's put it all together. The acceleration caused by the Earth's gravity is greater for objects closer to the Earth's center. This means the orbiter is trying to accelerate towards the Earth faster than the satellite. This extra acceleration causes the orbiter to want to fall away from the satellite, creating a stretching force along the length of the tether. And that's the force that keeps the tether taut and makes the tethered satellite go up. But how can gravity make something go up? Doesn't that violate the law of conservation of energy? Could we be getting something for nothing? To understand how gravity can make something go up, we need to go a little deeper into dynamics and look at the concept of center of mass. The center of mass is the point in a system where the system is evenly distributed and in balance. Balance, or equilibrium, is important because it means the system is stable. We're all in the same orbit around the Earth. Jeff, the orbiter, and these 2 apples. The center of mass between 2 objects, such as these apples, doesn't change just because they're in orbit. Their center of mass is between them, here. When I start them spinning, their center of mass continues to be in the same place. If I cut the string so the apples are attached by the longer string, the center of mass is still in the same place inside the orbiter, which means in the same orbit. What does this have to do with the orbiter and the tethered satellite? When the tethered satellite is in the orbiter's cargo bay, the center of mass is inside the orbiter. When we deploy the satellite, do you think the orbit of the center of mass changes? If it did, then we would be violating the law of the conservation of energy. However, like the apples, the orbit of the shuttle satellite system doesn't change because no external force has been applied to the system. But the positions of the orbiter and satellite do change to keep the system's center of mass in the same orbit and continue its stable equilibrium around the Earth.
Let's look at that concept in action on the ground.
To make a seesaw balance, one person sits in the middle. If we add another person, the one in the middle has to move to keep the center of mass in place.
It's the same for our tethered system when the satellite is extended.
Like the heavier person on the seesaw, the orbiter stays closer to the center of mass. Let's see how much the 100,000 kilogram orbiter moves away from the center of mass when the 500 kilogram satellite is deployed 20 kilometers. You could work this problem out for yourselves. Because the orbiter is more massive, it moves only about 100 meters away from the center of mass, while the satellite moves away almost 20 kilometers, and the center of mass of the system stays in its original orbit. Because the orbiter moves so little, it almost seems like the satellite alone is moving up. But now we know both objects are moving, one up and one down. Once you understand this principle, you can also see the situation is symmetrical. We could just as easily have made the satellite go down 20 kilometers and the orbiter go up 100 meters.
Here's another way of looking at it. Think of a pulley system. A heavy weight moves a little to balance a light weight that moves a lot. The weights can move in either direction. The center of mass stays constant. But in space, we don't need a pulley. A tether will do. Now let's look at the forces that keep the tether system stable along a vertical axis. When this toy is punched, gravity makes it return to a vertical position. The tethered system could also be perturbed off the vertical axis. Without any restoring force, the system would rotate like these tethered apples. But the tethered system's stable equilibrium keeps it aligned along a vertical axis. What causes the tethered system's stable equilibrium in space? Well, once again, gravity is at work. You see, gravity pulls on both ends of the system. The pull on the satellite at the upper end of the tether makes the system want to depart from the vertical, while the pull on the orbiter at the lower end makes the system return. Do you remember the gravity gradient? The end closest to the Earth feels the greatest acceleration, so the system feels a net torque and the tether returns to the vertical. It doesn't matter if the masses at the end of the system are equal or not. The gravity gradient is stabilizing the system. But gravity gradient is only part of the story. There's another force at work. Remember, we saw that there is an approximate force of 26 newtons for the gravity gradient over a 20-kilometer tether. Well, when the tether is extended 20 kilometers, our force measuring device measures 40 newtons, not 26 newtons.
Now, where did this extra force come from? Here is a clue.
It's the same force we feel when we wheel an object around on a string and the string stretches. The faster the speed, the harder the force tries to fling the object away from the center.
And this is what causes the extra force on the tether. As you have seen, gravity helps keep the tether vertical. And you can actually calculate this extra force. And it turns out it's about half the gravity gradient force. A significant effect.
Therefore, as it orbits the Earth, it is actually rotating once per orbit about its center of mass, creating this extra force that stretches the tether. We can see it in action another way. If we have one of our crews spin a bucket of water around in a circle, the water will stay inside the bucket as long as the motion continues. Stop the motion, the force disappears, and the water obeys the law of gravitational attraction. Like the gravity gradient force, it is also proportional to the length of the tether as long as the rate of rotation stays constant.
And speaking of constants, we've always assumed that the tether remains at a constant length, and this is not always the case. When we lengthen or shorten the tether, another physics principle that you've heard of comes into play, and that's angular momentum. You see it here in the motion of the skater. Angular momentum is the product of an object's rotational inertia and angular velocity about a particular axis. When the object changes its mass distribution, the angular momentum stays the same, but the rotation rate changes. We call this the conservation of angular momentum. And you can see for yourself how this principle works. Stand on a turntable with your arms outstretched and weights in your hands. Have someone start you spinning. Now bring your arms in. You speed up. That's because the more the mass is concentrated towards the center of mass, the faster the mass spins. Now, let's see how this part of physics relates to our spaceship and the tether satellite. When the tether is pulled in, the rotating mass of the system is concentrated into a smaller area, and the system tries to speed up just like the skater. When the tether is let out, the mass is distributed in a bigger area, and the orbiter and tether systems slow down, just like the student slowed down when she extended her arms. In the orbiter, we see this from a slightly different perspective because we are part of the rotating system. Remember, during most of the mission, for scientific reasons, the orbiter is moving with the tail forward. Do you notice how, from our point of view, the satellite moves forward with respect to our direction of motion and moves backward with respect to our direction of motion when it's let out? And this is called the Coriolis effect, and it occurs in all rotating systems as a consequence of the conservation of angular momentum. It is the tendency of objects in rotating systems to move in a curve as opposed to a straight line. We'll try to throw a ball from someone on one side of a merry-go-round to someone on the other side of the merry-go-round. As we can see, the ball is thrown in a straight line, but not from this point of view. Here it appears the ball's trajectory is curving. And this is what makes the satellite move backward or forward as we reel it out or in. The Coriolis effect is what makes hurricanes spiral and other weather systems curve. We won't go into the mathematics here, except to say that the larger the tether reel out or reel in rates, the greater the backward or forward motion of the satellite from the vertical.
So, let's review the aspects of tether dynamics that we've looked at so far. Gravity, center of mass, and angular momentum. All of these concepts are studied in your first-year physics course. Yet all of it is used in a way like nothing you've ever seen before. And there are even more uses of tether technology. On orbit, we found we could use the tether to generate electricity as the copper cord tether flew through the Earth's magnetic field. So the question left is, what can we use this tether technology for? We could use tethers to directly study parts of the Earth's atmosphere that we can't reach by any present-day technology. Tethers could reduce the need for chemical fuels in space, boosting objects to stay in orbit and assisting others to deorbit. And engineers could use the open wind tunnel of the Earth's upper atmosphere for testing the hypersonic aerodynamics of re-entry vehicles and aerobraking technology. It's even possible that one day, tether-driven electric cable cars will ferry space travelers from Earth to geostationary orbit. What uses of tether technology can you think of? The limits are not of physics, but of the human mind.